Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, today we've got a topic that might seem just a little bit crazy. Using loops in ladder logic. Using loops in ladder logic, ooh, that sounds like trouble. But in reality, if you follow some good programming techniques and you're careful and you do plenty of testing, loops are absolutely possible in ladder logic. And today we're going to show you how. Now, I am flying solo today as I've got to catch a plane as soon as we're done broadcasting. So let's take a quick look at how we're breaking down today's topic. Okay, we're going to, of course, take a look at loops, but we're going to start in computer programming languages before we actually dive into ladder logic techniques later. We'll definitely take a look at where applications are useful for these programming techniques, as well as give you plenty of demonstrations. All right, here we go. So, logic loops in computer programming languages, what are they? Well, effectively, you're talking about a sequence of instructions that are continually repeated until a certain condition is reached. That's one definition of a loop in computer programming languages. Now, there are different ways you can classify loops, different characteristics that loops have. Today, we're going to primarily talk about one characteristic of a loop specifically, and that is how many times a loop is repeated. If it's repeated a fixed number of times, that's one kind of loop. If it's repeated a variable number of times, that's another type of loop. Now, the types of loops we're going to take a look at are for loops. Those are loops which are typically repeated a fixed number of times. And we're going to take a look at while loops. And those are loops that are repeated a variable number of times. Now, in ladder logic, you don't have a for instruction. You don't have a while instruction. We're just going to show you how you can potentially mimic those relatively closely in ladder logic. Okay, so let's start with a for loop. Again, for is not an instruction you can find in ladder. Now, you can find it in computer languages, and you can find it in structured text, which is one of the IEC languages that are available. But today we're talking ladder. But if we were programming in IEC structured text, on the screen there, you can see the syntax for a for loop. Basically, built into the for loop is an index, which effectively is a starting and ending variable that through its value changes determines how many times you make your way through the loop. All right. So that effectively is a for loop. And generally with a for loop, as I mentioned before, you are executing a fixed number of times based on how you've set up the index. Now, generally exiting the loop is going to be the index reaching its maximum value. Now, in contrast, let's take a look at while loops. How are while loops different? Well, I'm showing you the syntax on the screen there. So effectively with a while loop, the statements that are in between the do and the end while parts of the syntax there, those are executed while the Boolean expression is true. And the condition being met or not met effectively is what causes you to exit from the loop. Now, one of the things about while loops, which makes them a little more dangerous than for loops, is that the potential for an infinite loop with a while loop is much higher than with a for loop. Why is that? Well, it's easier to accidentally set up a while loop with a condition which will never change. And therefore, if that condition is never false effectively, then you're never going to exit from that loop. So that scan, that particular scan that the while loop is executing on will never end. And therefore, you're going to have an infinite loop and your controller is going to reset. So we have to be much more careful anytime we are executing a loop a variable number of times to make sure that that variable number of times isn't infinity. why in the world would we even use loops? Where are they even useful in the types of applications that we might run into? Well, I've got 4 simple examples here that I'll describe in terms of useful applications. First of all, how about having a set of data and needing to perform an algorithm on that, like maybe an average, okay? Which means you need to handle all those values sequentially before you can find the average. So doing a loop might be a useful tool for that. And that actually is one of the specific examples I'm going to review today. How about searching a scanned barcode for a specific character? Maybe the starting character that we're looking for, maybe the ending character that we're looking for. Those are both great cases for using a loop, and we're going to show you specifically this example as well. And then a couple other examples. How about searching in an inventory list for a data match? That would be definitely a useful application for a loop, and that's actually one that we're going to cover next week as part of our topic next week, where we are executing and showing you how to use techniques to create lookup tables. But it involves a loop. But we'll cover that specific example next week. And then another example is printing archived data to a receipt printer. You know, maybe you've got a bunch of historical data for a particular batch that you ran on a machine, and you need to pull that data for all the various points, all the different batches maybe, and print them on a receipt. You might use a loop for that. Okay, so that's just 4 examples of where loops could be pretty useful. Okay, so now let's talk about techniques for creating loops in ladder logic. And I'll reiterate, there's no for instruction, there's no while instruction, but we're going to kind of mimic the execution in ladder. So let's start with a for loop. And remember, a for loop is the loop where we know we need to execute a certain set of instructions a set number of times, 10 times, 5 times, 20 times, but a set number of times. So what are the steps we're going to follow when we kind of mimic a for loop? Well, we need to start with an index, so we need a variable. We can call it index or we can call it something else. We need to identify where the top of the loop is in our ladder logic, okay? And we're going to use a special instruction to do that, which I'll talk about in a minute. We need to execute the instructions that are to be repeated, okay? Whatever those happen to be, all right? We need to increment our index, okay? So the index that counts how many times we've gone through the loop, we need to manually increment that in ladder because it doesn't automatically happen on its own like it would with a for loop. We need to test the index. Have we reached the maximum number of times we want to go through our loop? Yes or no? And then if we still need to go through the loop more times, we need to jump to the top of the loop. Or if we've already gone through the fixed number of times, we need to exit the loop. So those are effectively the steps we're going to take to mimic a for loop. Okay, now let's talk about some key instructions that we need whenever we're executing loops. And these instructions are going to be important for both mimicking a for loop and a while loop. All right, so let's start with the label instruction, which you see highlighted there at the top of this ladder snippet. The label instruction can be used a couple of different ways. You can use it as just a handy way of labeling a section of your logic if you wish. And you can put labels throughout your logic just so that as you're scrolling through your logic, it's easier to find and identify different sections. But really the way labels are most useful is to label a section or a spot in the program where you want to be able to jump to, whether that's jumping forward to it to skip over a bunch of code or jumping backwards to it to execute code over and over again, like in a loop. So that's the label instruction. And then there's the jump instruction that you see highlighted at the bottom there. That's the instruction that when it's executed causes the program to jump either forward or backward to the label that's been specified there. And in this snippet on the screen, you can see we're jumping backwards. Now, another instruction that doesn't necessarily have anything specifically to do with loops, but is used very often when you're doing applications that require loops, and that is this. That's the indirect move. The indirect move is a move block where either the source or the destination might be a pointer instead of an actual fixed location or a fixed variable. Okay, so in the example I'm showing there on the screen, all right, we have a source which is a array, okay? And therefore, it requires an index into the array or a pointer into the array so we can retrieve one of the array members. And then in this particular example, we're copying whatever that member value is into another variable location that's just a fixed location, and that variable in our example on the screen there is called extracted value. So what you're seeing on the screen there is we have an array called source data. The index variable is going to be read at execution time. It's going, whatever its value is going to be the pointer to the index into the source data array. And then that specific value at that specific location will be copied over to the extracted value variable. So that's what's happening on that particular instruction that I have there on the screen. And what you'll find is with a lot of the applications where you're doing looping, you're acting either on a set of data or an array of characters or something like that. And therefore, using an indirect move where you're varying the pointer into the array is a very common application. So I thought I would highlight it here. Okay, so let's take a look at our first example. And that is an example that we're going to create using loops, which is going to be used to calculate the average on a set of analog values, okay? And specifically what the loop is going to be doing is it's going to be used to calculate the sum. Because remember, when we calculate an average, we have to create the sum of a bunch of values, and then we have to divide that sum by the number of values, and that's how we get our average. So the part where we're going to be doing our looping is actually going to be doing the sum. Okay, so let's kind of walk through the steps here, and then I'll show you the real-world application, both in Cscape and on the bench. Okay, so we've got a series of analog values that we've captured, and they could be stored in a series of R registers, maybe if we're using register-based ladder, or they could be stored in an integer array, all right, if we're using variable-based ladder. And our example today is going to be using variable-based ladder. Now, we're going to be creating a loop that finds the sum of all the stored analog values. So it's going to go through the array and it's going to retrieve the values one by one, and it's going to add them all up. All right. And the instructions we're going to be repeating inside the loop are going to be the instruction that retrieves an analog value from the list, the next one that needs to be added. We're going to have a add instruction that needs to be inside the loop. And we need an increment instruction or another add instruction to increment the index. All right. And then once we're done with the loop, in other words, once we fall out of the loop and we've calculated the sum, then we can just take that sum and divide it by the number of values in the list, and that will give us our average. Okay, so let's head over to Cscape, and let's take a look at the logic we've created to execute this application using a loop. All right, so let's start with our main area of code here. So let's just examine the start here, all right? Because this is the code in our main routine that is going to be calling a subroutine. Now, I've decided to put my logic for finding the average in a subroutine. You can absolutely have loops in your main sections of logic. They don't have to be in subroutines. It just made a lot of sense in this particular example to make it part of a subroutine. Okay, so what I have happening in my main logic is I've got a push button on the touchscreen that is pressed. It creates a one-shot, a positive transition coil. It calls a subroutine, okay, called average value. And this is the code in this subroutine that actually executes the code to find the average. Okay, so let's go through that code now. Okay, so you can see the label instruction here. Now, this label instruction is labeling the top of the subroutine. And remember, that gets added every time automatically when you create a subroutine. So that's another use of the label instruction. It's also kind of one of the components that are built into subroutines. All right, but in this case, here's what we're doing with our code. Okay, so generally what needs to happen anytime you're going to be doing a loop is usually right before the loop starts, you need to do initialization. So that's what we're doing here, okay? So I've got a variable called index, which is what we're going to increment to keep track of how many times we're going through the loop. And I need to have that starting at 0, all right? Because what's going to happen is inside my loop, I'm going to be incrementing this, but I need to make sure it starts at 0. So I'm initializing the index variable to 0. I'm also initializing my sum variable to a 0, because remember, that's what I'm finding inside my loop is I'm going to be finding the sum of, as it turns out, I believe 20 analog values that have been stored away in an array. So I need to zero that out as well. So initializing variables is a very common type task you need to do at the top of before you get into a loop. All right, next we've got our label, and this label is labeling the start of the loop. And I gave it a name called sum_loop, so I could remember that, hey, this is the start of the loop. But it doesn't have to have the word loop in it or anything like that. But I did identify this as the start of the loop. Okay, so at the top of the loop, what are we gonna do? Well, we're effectively gonna execute an indirect move, all right, and we're gonna retrieve a value based on the index from that value list, all right, and we're gonna take a value out and we're gonna copy it into another variable called value, all right? Now, it turns out that there are 20 members in this value list, and the index needs to be incremented from 0 to 19 so that we can point at the 20 different members of the array. Remember, arrays are 0-based, all right? Okay, so we're going to retrieve a value one at a time and store it in a variable called value. Then we're going to take that value that we've retrieved and we're going to convert it to a double integer. Why are we doing this? Well, we're taking 20 integer values and we want to sum them all up. Well, we could have overflow issues if we, just sum them up into an integer. So I'm converting the value we're taking out into a double integer so that the sum that we're creating is a double integer. That way we won't have any overflow issues by overflowing an integer value. Okay, so we retrieve the value, convert it to a double integer, do a double integer add of the new value we've just retrieved to the sum. Now the sum starts out as 0 the first time through the loop, but it will build on itself every time you go throughout the loop, okay? So this is what we're repeating inside the loop. Now we've got a little bit more work to do inside the loop, and that is we need to increment our index, all right? And then we need to test the index to make sure that we're still less than 20, because remember, we want to vary our index from 0 to 19. So if this were a for loop, it would be something like for index equals 0 to 19, that sort of thing. All right, but as long as we're less than 20, we're going to execute our jump function and jump back into the loop. And then once we're done and the index has incremented to a value of 20, this won't be true anymore. We'll drop out and we'll simply take our sum, double integer, divide it by 20, which is how many values in the list, and we'll come up with our average. Okay, and then we'll return from our subroutine back into our main routine. All right, so that's what's happening with our logic. Now let's take a look at what's happening on the bench. Okay, so here I have the test value. So these are the 20 members of the array. All right, I've got that button at the top right there, which I can press to cause the subroutine to be called. That will calculate the average. So let's see what happens when I hit the calculate button. Okay, so it calculated the average, as you can see, happened, from the naked eye standpoint, it happened really fast. And there we've got our answer. Okay, it's an answer as a double integer, as it turns out, but you can see that's pretty much where the value falls. Now, if I were to, let's say, turn one of the values to a 0, I should see the average drop on the next time that I calculate that. So let's try that. And sure enough, when we zeroed out one of the values that was 3,000 before, our average dropped significantly. All right, very good. So that is our first example where we mimicked a for loop in ladder logic by executing a loop a fixed number of times. All right, now let's head back and let's talk about mimicking some aspects, at least, of a while loop. All right, so in this case, what do we need to do when we're mimicking a while loop? At least most aspects of a while loop. All right, well, again, we need to initialize an index, okay, because why do we need an index in a while loop? A while loop doesn't have an index. That doesn't make any sense. Well, if we want to be safe, okay, there's two reasons we might want an index. First of all, we might want to have a safety net of a maximum number of times that we're going to go through the loop. Okay, and we can use an index as a safety net. Let me give you an example. Let's say we're searching a big inventory list that has 100 elements in it, and we're looking for a specific value. So, we're looking for that value to tell us to drop out of the loop. But what if that value is never found? What if that value we're searching for doesn't exist? Well, we don't want to have an infinite loop there, all right, because our condition is never met. So what we can do is we can have an alternate way of dropping out of the loop by utilizing an index, all right? So that if we know there's 100 members in our inventory list, we don't want to search the entire list every time. We just want to search until we find what we're looking for, unless we don't find what we're looking for, and then we want to drop out safely. So that's an application. Even though we're kind of mimicking a while loop, where having an index is useful. Now, the other reason why an index is useful is because, let's face it, most of the time when we're executing a loop, we're also searching through a list or something, or an array, and we need an index for the array anyway. So we might as well create it. So we're going to create an index, all right, and we're going to initialize it wherever its initial value needs to be. We'll label the top of the loop like we did before. And we're going to execute our instructions that we want to repeat. And then we're going to test our condition that's going to cause us to fall out of the loop. In other words, that's ultimately what we're looking for to fall out of the loop. If we're searching through a big list of 100 items, if we find our item, we're done. Why look at the rest of them, right? So let's just fall out of the list. So the condition will cause us to fall out of the list. So that's an important part of mimicking a while loop. And then if we've met our condition, we're going to exit the loop. If we haven't met our condition, we'll increment our index so we can look for the next value, or look in the next part of the array, or just make sure that we don't execute that particular task indefinitely. All right. And then the last thing we're going to do is jump back to the top of the loop if we had no reason to exit. In other words, if our condition wasn't met and our index hadn't reached its max, then let's go ahead and jump to the top of the loop. So that's what we're going to do to kind of mimic a while loop. So yes, we're adding an index there, but that's for safety purposes and generally for practical purposes if we're dealing with a list. Okay, now the specific example I'm going to show you today is I'm going to show you an example where you're going to search a barcode for a specific character location. So let me describe this to you. So let's say we've got a barcode coming in. It's 32 characters. We've scanned it with our barcode reader, but all we know is that somewhere in those 32 characters, there is a part identifier. And there's a specific character that we know is the beginning of the part identifier. Maybe it's a Z or an X or a V or who knows what it is, but a specific character is going to be the beginning of the part identifier. So what we're going to do is this. Our barcode string is going to be stored in either a series of R registers, 2 characters per register, if we're using register-based ladder, or if we're using variable-based ladder, we use strings as bytes. So you'll have a byte array, and if it's 32 characters, it would be a byte variable with 32 elements in it, okay? So we're going to create our loop that's going to basically retrieve a character one at a time from the barcode string. We're going to compare it against a target character, the character that we know starts the part identifier that we're looking for. And then again, we're going to increment one by one looking for that character. If we ever find the character, we're done. We want to drop out of the loop. If we don't find the character and we get to the 32nd location and we still haven't found the character, we want to still fall out of the loop, but we're going to do it because the index has reached its maximum. Okay, so that's effectively what we're going to do. And at the end, we're going to report that character location where we found that character. And if we didn't find it, we'll report something that's obviously wrong, like -1. So -1 will indicate that we didn't find the character, for instance. Okay, so let's head to Cscape and let's take a look at our code required to more or less mimic a while loop. All right, so once again, we have some simple code here. Once again, it's a push button on the screen, triggering a one-shot, triggering a subroutine. Again, you don't have to put loops and subroutines, but that's what I did here for these examples. All right, and then so we're going to call this subroutine that I've named find character. So we'll go over here to the find character subroutine and examine that a bit. Once again, there's a label built into every subroutine that labels the top there. And as before, we have initialization we need to perform on any variables before we jump into the loop. So once again, we're going to set our index where it needs to be. And in this case, we're going to set a variable called character location to a value of -1. So ultimately, if we find the character we're looking for in the string, this value of -1 will be overwritten by something else. But if we don't find the character in the string, in the barcode, then it'll remain at a value of -1. That way, the program will know, oops, that character was not found. All right, now let's take a look at what's going on inside the loop. Here's the label that identifies the start of our loop. Here we once again have an indirect move. This one, we're retrieving a character from our barcode string of 32 characters, starting at the first one with an index of 0. We're moving that individual character, which is a byte, into a variable called value to test. We're checking to see if that value we're testing is equal to the target character. So that's the character we're looking for that tells us we found our part identifier beginning. Okay, and if it is found, if it does match, I should say, we're going to turn on a bit that says match. All right, so that we know, yep, our condition has been met for falling out of the loop. All right. All right, now what happens next? Well, if we didn't find a match, all right, we don't want to fall out of the loop. If we didn't find a match, we need to increment our index and make sure we haven't reached the end of the string. And if we haven't, then we're going to jump back up to the top of our loop, take a look at the next character, etc., etc. So we'll either fall out because we found the character we're looking for, or we will fall out because we reached the end of the string because our index hit its maximum value. And then at the end, after we fall out of the loop, if we did indeed have a match, we're going to copy that index value, which is the location we were pointing at when we got our match, as our character location with the character that we found. All right, so now let's take a look at the bench and let's go through this example. Okay, so I need to change screens here. Okay, so there you can see my barcode scan at the top that I've simulated. Okay, a bunch of characters and numbers and those sorts of things. And then I have a place I can plug in the part identifier that I'm looking for, and then a place where it's going to tell me what that starting location for that part identifier is. Okay, so let's say the part identifier we're looking for is an F, as in Frank. Let's take a look there. Okay, well, the first location is where the character is found. So an index of 0, not a 1, an index of 0 is actually pointing at the first character location. Well, let's say that the part identifier wasn't an F. Let's say it was a Z instead. Okay, we've returned an index of 4. Because again, we're counting from 0 with arrays, and the Z is the 5th character, which means an index of 4. So as you can see, a very practical application for using a loop. Now, what would we do with this once we found the location? Well, if our part identifier always started with a Z and had 5 numbers after it, then we could use the starting location as a very easy way of extracting the part identifier from that barcode scan with another instruction or another little bit of code. So again, I'm just showing you the part of the code where you would use an actual loop. All right, so I believe that wraps up our demonstration for this week. So this is the part of our program where I remind you that we are here every Tuesday at 2 o'clock, whether we are fully live or whether we are pre-recorded. Because either way, we always have someone standing by to answer any questions you might have. Now this year, we are celebrating the 10th year of Horner Lighting Group products. Don't miss their great videos alongside our automation videos on the Horner YouTube channel. Okay, now the training schedule has now been announced. It's now up on the website. We do have the dates figured out, and here they are on the screen. Now we may add additional courses based on demand and a number of other factors, but these are the ones that we've announced thus far and the ones that you should count on. So don't count on us adding more, although it's not out of the question. Okay, so next week, I'm going to show you a technique that you can use for using what's called lookup tables in ladder logic. So this is a technique that's really useful for tasks which might otherwise involve complex math or maybe searching through a list or something like that. Using lookup tables is definitely a technique you should be aware of. Okay, if you haven't done so already, don't hesitate to subscribe to our channel. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay. All right, so until next week when we talk lookup tables, let's all get out there and do us some good.